Okay, so my name is Yoav Freund. I'm a professor of computer science here in UCSD, and I'm going to tell you about drifting games and online learning. Okay, so this is the plan of the talk. I'm going to first tell you about some learning games, online learning games. Then I'm going to switch to decision theoretic online learning, which is another kind of game, which is much more popular these days. And then I'm going to go from there to continuous time limit and the heat equation, and the normal hedge and stochastic differential equations, open problems. So the first half of the talk, I'm going to be pretty detailed and I'll explain everything. In the later part, with the continuous time limit, I'll be pretty brief. I'll be happy to take questions, but many of the things would require a long time to describe. So if I can, I will describe them. Maybe I'll use the whiteboard, even though I'm not sure the whiteboard would be available to those on Zoom. Anyway, I have my chat open, so you feel you can ask questions. Also, you can just speak up. Okay. So starting with online learning games. Online learning games are, in this very simple case, we're talking about predicting a binary sequence. So 0, 0, 1, 0, 1. And then we want to predict the next bit. And to do that, of course, we need some help. So we have the help of experts. So experts are themselves generating predictions of what the next bit should be. So the first expert says it's 1, the second expert says it's 0, and so on. And we want to somehow combine the prediction of the experts for bit t and come up with our prediction for bit t. Okay? And then to think about it really as a game, it's something like this: an iteration t. The experts give their predictions. Then the learning algorithm chooses its prediction. And the adversary chooses an outcome. Everything is game theoretic, so there's no statistics here. And the algorithm and the expert incur loss 0 if it's not a mistake, and 1 if it's a mistake. Okay, and the goal is that the total number of mistakes made by the algorithm is not much larger than the number of mistakes made by the best expert. Okay, so one of the experts is going to turn out to be best at the end, and you want to be almost as good as that. That's the goal. That's called minimizing regret. Okay, so let's start very easy. Let's start with the halving game. So what is the halving game? You have n experts, and one of them is perfect. Okay, so one of these experts makes no mistakes ever. So the learner strategy is pretty simple. There's a pool, which is the set of experts that have made no mistakes so far. That's the experts we want to follow because the other ones are just ignored. And then the prediction is to go with the majority of those experts that are in the pool. Okay, simple enough. So when the learner is wrong, then the pool size is reduced by at least a factor of 2. So that means that you make at most log 2 of the mistakes. Very straightforward. Now, the adversarial strategy is to split the pool to 2 equal size sets. That's the best thing that the adversary can do. So here's like a little figure to explain this. I'm going to spend some time on this very simple one, just to introduce the notation and terminology. So we can think about two bins, like one that is the pool and one that is outside the pool. And basically, the pool is split into two, those that predict 1 and those that predict 0. And then depending on the outcome, the next configuration is either that you have 3 in the pool or that you have 2 in the pool. Those are the two possibilities. Okay, so the equalizing strategy for the adversary is if the pool size is even, then the adversary can split into 2 equal parts. Right? That's fine. And in that case, the size of the next pool does not depend on the learner's choice. Right? Basically, it's an equalizing strategy. It makes both situations exactly the same. If pool size is odd, then the next pool does depend on the choice of the learner. And the learner would choose, of course, the smaller set because it wants to finish the game as quickly as possible. Okay. So we're going to make a little twist. We're going to basically, instead of thinking about the experts as discrete things, we're just going to think about them as a continuous thing. Or to say it more formally, the adversary can split any set into 2 parts at any fraction that it wants. Okay, so in this situation, the adversary can always do the optimal thing. So just in terms of notation, in the discrete game, we start with n experts and we end with 1. And in the continuous game, it's more convenient to start with 1, that's the mass of the experts, and to end up with epsilon, that is 1 over n. Okay. So the equalizing strategy is optimal. The choice of the learner is irrelevant. If the adversary plays suboptimally, then the player should make the better choice under the assumption that from now on, the adversary will always play optimally, right? So basically, okay, it made some foolish decision now, but it's not going to make foolish decisions again.
Yoav, can I ask a question?
Yeah.
At the beginning, you had one expert that never makes a mistake. But if the adversary has access to the predictions of the experts, can't the adversary always make the expert that never makes a mistake make a mistake?
No, it can do that as long as basically there is that you haven't identified the expert that doesn't make a mistake. Right? Basically, your pool includes all of those that might be that expert, and because you assume a priori that there is something in that set, then the number of mistakes that you can make is at most log 2 of n.
Okay.
Okay. So, right. So now I'm going to introduce a probabilistic interpretation that for this very simple case seems like way overkill, right? Like we all understand what is going on, but it's still useful, will be useful in the future. So let omega, the sample space, be the set of all experts, and a single expert is an element in omega. Okay, so the SI of omega is the prediction of expert omega on iteration I. Li is the prediction of the learner on iteration I. OI is the outcome of iteration I. And because we're going to assume a worst case, we assume that Li is not equal to OI at every iteration. Right? If there is a iteration on which the master doesn't make a mistake, then the adversary just lost another step. So we're just concentrating on these. Okay, so we can think about these indicator functions. The EIW is 1 if SIW is not equal to OI, express omega errors on iteration I. And the pool is simply the set of experts that have not made any mistakes so far. The equalizing strategy in this sense is this strategy that basically says the probability of SIW is equal 1, given the past actions, given whatever was done so far, is equal to half, okay, independently of anything else. So you can define these things that would be useful later. First of all, the state of the game. So the state of the game in this simple game is just the size of the pool, okay? So the set of experts that made no mistake. And it's important to think that the state holds all the information that you need. You don't need to know how we got to this state. Right, so that's the score is the probability of this set. Okay, so that's the score in this case. And the learner's guarantee is that the score at iteration I+1 is at most half the score at the previous iteration. And the equalizing strategy guarantees that it's actually equal. Yeah.
Sorry,
Yes.
what's the probability over? What's random?
The set of experts. So there's nothing random, nothing is actually random. That's the sample space. We're playing over the set. We're playing over distributions, essentially. So there's nothing random in it. It's basically, it's just the probability is literally the number of experts that you have in a state, in the pool. Okay, so the game ends when this is smaller or equal to epsilon. And the min-max solution is that n is log 2 of 1 over epsilon. So we just did the same thing, just much more complicated. Okay, so here is where it will start paying off. Binomial thing. So suppose that at least one expert makes it most k mistakes. Okay, so it's not that one expert is perfect, but one expert makes it most k mistakes. So now we can also draw it as a picture like this with bins, but now we have k plus 1 bin. Okay, so k, the index of the bin is how many mistakes has that expert made. Okay, and we assume that something that at any step there is something that is in the bin, and we're basically ending the game when there is one expert that made k mistakes. Right? At that point, you're not going to make any more mistakes because you're just following that expert. Okay, so again, we can think about it with this figure about going the two ways. Basically, I denote with two colors, I denote those experts that predict 0 and those experts that predict 1. Okay, and now if the outcome is 1, then the new configuration is this. When the outcome is 0, it's a mistake. We're always only concentrating on mistakes. Then the new configuration is that. Right? So either the red moves one step up or the blue moves one step up. Okay. So once we've done that, we can just think about this as the configuration. We don't need to remember the colors. Okay, so that's essentially going to be our state. Okay, so what's the optimal strategy for this game? It's very similar to the previous. Basically, each bin we're going to split into two equal parts. And again, we're assuming divisibility. So it's not a discrete. So here is our mass of experts at a particular configuration. And the best thing for the adversary to do is to split each of the bins into two. And then if the outcome is, if the learner is 0 and the outcome is 1, then you get this configuration, and otherwise you get this configuration. Okay, but if you ignore the color, it's the same configuration. Okay, so we're in the same situation as we were before, where by doing that, we're kind of doing the equalizing adversary. Okay, so now you'll see that it's worthwhile to use this terminology that we introduced. Interpretation is a random process. So the equalizing adversary splits each bin into two equal probability subset. And the number of mistakes by expert omega at iteration I is Li omega. And the fraction of expert with J errors at iteration I is simply Pij, which is the probability of Liw for J under this probabilistic interpretation. Okay, so the state is simply how many experts we have in each bin. And again, it's continuous state. Okay. Continuing with the interpretation, in this case, the score is the probability of good experts at the final iteration. There is going to be a final one where we have a mass of at most 1 inside the bins, and a good expert on iteration n, given that the state currently is phi, and assuming equalizing adversary from this iteration on. Just exactly the same that we did before. And now it's the probability that Ln omega is smaller or equal to k given the current state. Okay. So basically, what's the probability? So this is the probability that you are in bin, in the final bin. Sorry, at time n, this expert has at most k mistakes. Okay, so what's the initial score? The initial score is this probability that ln k smaller than k is with the initial state. So the initial state is everybody at 0 error. So with no additional information. And the final score is is basically just the sum of the probabilities of the total mass of the experts that is that is made at most k mistakes. Okay, so solving this recursion, you get what we call binomial weights. So we get that there is a potential function, that's a new thing that I'm just describing, that is basically this conditional probability. Okay. And the score is simply the weighted sum of these potentials. Okay. And then basically the strategy for the learner is to choose a prediction such that if the mistake is, if it makes a mistake, then the score is smaller. Right? So it wants to basically choose the one with a total score that is smaller. We can express this a little bit differently. We can, instead of looking at the total score at the next time, we can basically see for each bin how much is the score different if you take one action and the other action. And that's basically this difference. And that gives us these weights. These are the binomial weights. And in this case, the learner chooses to predict with a set of experts that has larger weight. Okay, so the larger weight corresponds to the smaller score. These are the experts that matter the most. That's their weight. So that's the potential. The nice thing is that we can define this potential recursively, just because of the properties of the binomial. We can just say that phi I jn is equal to the average of phi I plus 1 jn and phi I jn and phi I plus 1 j plus 1. Okay, so the potential is basically, it has probability half going this way, probability half going this way, so you just take the average. So that's the evolution of the potential. You see that it basically goes backward in time, right? If I know what is phi at I plus 1, I can calculate phi at I. And the weight, as I said before, is the difference of the potentials. Okay, so this is something that is going to reappear. So basically, we have a potential that has a time evolution that is basically averaging, and there is the weight that is the difference between potentials. So what is the binomial weight algorithm? The learner predicts with a set of experts that has the larger total weight. If the number of algorithm mistakes is n, that satisfies 1 over m is larger or equal to this weight, then basically you have this recursion, that you have that this is the initial potential. The potential never increases along the iteration, because you always choose the smaller one. Maybe they're both equal, so it's just equal. And then at the end, you have exactly what you wanted, right? So basically, you have that 1 over m is the total mass that you have inside the good part. So the maximal number of mistakes for n expert, when there is at least one that makes most k mistakes, is smaller than n, the smallest n that satisfies this equation. If m times n smaller or equal to k smaller than 2 to the n, then that n satisfies your equation. That n is the number of mistakes totally that you can make. Okay, so what does this look like? And this is again min-max, assuming divisibility. If you have divisibility, there is a strategy for the adversary to split all the bins into equal parts, and a strategy for the learner that when the adversary is not min-max, that guarantees that this is the number of mistakes. Now, what about if it's not divisible? So it turns out that this relates to another problem of Ulam's game with K's live, which I'm not going to talk about. But Spencer in '95 showed that if the number of chips, the number of experts, is 2 to the 2 to the k, so that's a huge number relative to k, then this is still min-max. But you need a lot. I'm kind of going beside that because I'm just saying, no, they're just continuous. And this is kind of how at the typical step, the potential and the weight look. Potential is like this wave, this kind of like error function. And then the derivative is kind of like the normal distribution, or binomial distribution, right? And basically, it's kind of interesting if you think about it, because in other algorithms that we'll talk about, the weight will always increase as you as the number of with the number of mistakes. Here, because we have a known bound on the number of mistakes of the best expert, at some point it's better to give up on an expert, right? And that basically is represented by this going down. So it's a very, very different algorithm than the other multiplicative weights algorithm that we're going to talk about. And what you can think about is that this potential is kind of pushing the experts to go above K, right? So this starts pretty flat and becomes sharp. Okay, so far for this simple games. Now I'm going to go to more realistic games. So this is the decision theoretic online learning. And in this case, it is a much more pared down kind of game. There's no prediction and outcome. There's only actions and losses. Okay, and so we have access to n actions. At iteration t, the algorithm chooses a distribution pt over the actions. And each action has gain or loss, let's say in the range -1 and +1. The algorithm's loss is simply pt weighted sum of the action losses, so the dot product. Okay. So think about it as a game. On iteration t, the learning algorithm chooses pt, and the action I gains gti is in between -1 and 1. The algorithm gain is pt, the dot product, pt and gt. And the goal is to minimize the worst case regret. Okay, so we want to be almost as good as the best action in hindsight. So this is the regret. The regret relative to expert to action I is the gain of the action minus our gain. The difference between the gain of the action, and then we are taking the maximum RIT. We want to bound the maximum to this. We want to say, in hindsight, the difference between our gain and the gain of the best action is small. Okay. Again, there is nothing statistical. Okay, H is an algorithm for this. And you define a weight. This is essentially the same weight as we talked about before. And the weight is simply e to the some learning rate eta times the cumulative gain. So you give exponentially more weight to things that have large gain. And you define the distribution by normalizing it. And what we know about this algorithm is we know that if we know the length of the game a priori, then we can choose the learning rate such that max regret is square root of 2 ln n plus ln n. And there is a lower bound that is almost completely timed. Okay? So in some sense, there is nothing else to do in this problem. But there are remaining questions. So what if we don't know t ahead of time? You can use doubling trick, but that is pretty wasteful. I mean, that's not the way that you want to go. And then the question is, how did we come up with these exponential weights anyway? I mean, why exponential? No clearer. We just came up with it.
you all.
Yeah.
The lower bound is, proved by just finding a bias, find amount, and that type of formula.
Yeah. Basically, you have one coin that is slightly better than the other coins. And you can show that the gap is, that you can't do, that the gap to that coin, basically that you can't identify this coin. Right? That's enough. Okay, so that's one issue. Another is that when n is very large, we might want to have regrets that are relative to the best epsilon rather than to the best expert, right? If the expert number is huge, you want to say I'm almost as good as the top 1%. Okay, so to answer these questions, we go back to drifting games. So what I was telling you before, I'm kind of hiding a lot of literature. There's basically this was one of the examples, the binomial weights was one of the example of drifting game. Boost by majority was another example of drifting games. And then Rob Shapiro wrote a paper about drifting games. Then that continued from there. So we're basically just going to that methodology that we used before. Okay, so how are we going to use this methodology? We're going to now make time continuous, right? So we made the experts continuous to make them divisible. Now we're going to make time continuous. So I call it getting off the grid, right? Before we worked on the grid. Now instead of making or not making a mistake, we're suffering any loss in -1, 1. So now our picture looks a little different. And we don't want to specify a priori the number of mistakes of the best expert. Okay, so the picture is more like this. You have at any point of time, you have your experts or actions, whatever you want to call them, they have their own loss, and then you have the algorithm. It has its own cumulative loss, and now the algorithm puts weights puts a distribution over the actions. It's clear to see that if these actions have the same cumulative loss, you'd put the same weight on them. So it's really on the locations rather than on individual things, individual experts. And then you suffer the losses. Okay, so this has a little gain, this has a little loss, and this has a big loss. Big gain, sorry, big gain. And so now the algorithm, because of these weights, has its own gain. And so now you are in a new configuration. Okay, so everything moved according to these arrows, and now you have a new configuration. And you want to basically understand the dynamics of this game. So I call it the continuous time heuristic because so far we don't completely know how to move from, this is a heuristic for how to build potentials. We don't know of a simple way to get from this heuristic to an algorithm. There's all kinds of hacks, I would call them. We're now just looking at this heuristic that says, okay, suppose now that time is continuous and the losses are continuous. And so we basically want to look at what happens in continuous time. Okay, so we want to use the potential-based algorithm in analysis. And we need a potential that is defined for all the reals. And the idea is to take the time limit, so make the number of steps go to infinity, and the size of the steps go to 0. Right? number of steps goes to infinity, the size of the steps goes to 0. Basically, we're going from random walk on discrete to Brownian motion. So instead of I going 1 to n, we have time going 1 over n, 2 over n, up to 1. And then delta t is 1 over n. And the strange thing is instead of the step going +1 or -1, or 0 or 1, more exactly, now we have plus square root of delta t minus square root of delta t. That's kind of like strange, right? It seems like it should be just plus delta t minus delta t. But the problem with plus delta t minus delta t is if you do the calculation, you'd see that the variance of this process goes to 0 as delta t goes to as n goes to infinity. And so you basically you need this kind of weird scaling, and that's the scaling that of Brownian motion. Okay, so any other scaling would make the variance go to 0 or go to infinity. So to keep things working, you basically need to do this scaling. Okay, so let's look at what our potential recursion looks in continuous time. So the integer recursion, we just have this, right? Just basically averaging the two. In the scaled recursion, we have this slightly more complicated thing. So instead of time plus 1, we have time plus delta t. In terms of s minus 1, we have s minus square root of delta. Okay, so that's simple enough. Now we can reorganize this a little bit. So we can reorganize it a little bit by subtracting phi of t plus delta t from both sides. We subtract here the phi of t plus delta t from the phi t, and we subtract here phi of t of delta t. We have to multiply it by 2 because there's a 2 here. Okay, and we divide everything by delta t. Why? Just because. Okay, so that looks ominous, but if you really look at this a little bit carefully, this is just the gradient of phi. And if you look at this carefully, this is the second derivative with respect to x. So you get a differential equation that looks like this. So d to dt of phi ts is equal to minus half d to ds squared of phi ts. This is called the Kolmogorov backward equation or the heat equation. So somehow when we make now time go to infinity, everything becomes very clean. Just like before it became very clean when we made the chips go to continuous. Okay, so that basically tells us what kind of potentials we should use. Right? Give me some boundary condition, I can calculate the potential as a function of time. So now I'm going to talk about normal hedge. So what kind of solution do we have for this? Oh, this above. What kind of solution? So the solution that we want is positive, increasing, and convex. We don't want, so the usual solutions to the heat equations are things like Gaussian, but we're not interested in those. We want solutions that are positive, increasing, and convex. And so they kind of explode. So one solution is essentially hedge. Okay, so it's hedge, but with a little bit of a tune here, minus eta square root of t. That tuning doesn't matter to the algorithm itself because that is basically normalization in terms of hedge. So it's essentially hedge. This form of hedge was actually found by Chernoff and Vogt. And the other solution that we know of is basically normal H, where you would say the solution is 1 over square root of t, ignore the plus 1, that's just details. 1 over square root of t times the exponential of r squared divided by 2t plus 1. It's 2t. And if it is negative, it is basically the potential is constant, which means that the weight is 0. Right? So every expert that is worse than the algorithm is just ignored. So what is the advantage of this algorithm relative to the ones before? And there have been many variants of this since we published it. First of all, it's much more aggressive than hedge. For me, this is the most important thing. It is slightly worse bound than exponential weights, but you have a bound that holds simultaneously for all epsilon and all t. Right? There's no learning rate to tune. Right? So here there's a learning rate, doubling trick or other tricks. Here there's just no learning rate. It's kind of baked into the algorithm. Okay, so this bound for this one algorithm holds without any tuning for every epsilon and every t. So it's essentially the same bound that we have here. Sorry, have here square. Oh, yeah, I forgot the square root. Yeah, that's a typo. So for the square root of t lambda. Okay, so now we go to SDE. So this is very recent stuff. So the heat equation characterizes the time evolution of the distribution over the regress. But what about the time evolution for a particular expert? Right, so if you just follow a particular expert, how does that behave? So that is characterized by stochastic differential equation. Okay, and the idea of it I had in 2009, but I didn't really know how to work with it. I didn't understand enough about SDE. Recently, these papers actually use SDE to come up with bounds. And so this is very exciting because it's a whole new set of tools that you can apply to this problem. So yeah, so it's a more refined tool that yields tighter bounds. Okay, so finally, open problems. So the open problem that interests me the most is, can you replace t by something that is like v of t? What is v of t? V of t is a cumulative second order quantity that depends on the squares of the instantaneous regress. Okay, just to make you realize that this makes sense, is just think of the changing the range of the losses from -1 and 1. So let's say that's the range, but let's say that the adversary always plays plus half minus half, right? So you want the bound to depend on what the adversary actually did, rather than on the 1 minus 1 plus 1. So that's the type of things that is here, and it actually connects very much in stochastic differential equations to the concept of cumulative square variation, or I think it's called bracket process. So that's like where I'm talking with these guys right now about this. Now the different question is, okay, so we have 2 points on this solution of the differential equation. We have hedge and we have normal hedge. Is that everything? It can't be everything, right? Because this is a huge space. This is a linear space, right? So any combination of 2 solutions is a solution. So are there better solutions better solution than the normal hedge? Is there a best potential solution? And there's a very obvious kind of lower bound on this case, which is Brownian motion itself. So Brownian motion gives you a lower bound on how much you can do. That's exactly the expert that everything is random. And the question is how close you can get. Really don't know. Okay, so this is the end. And just as an advertisement, I'm teaching a class on online learning next quarter, and it's DSC 291, Topics in Data Science Online Learning.
Hello, game. Give some examples, practice, like this kind of experts and the adversary.
For the action, it's very easy, actually. It's like, let's say, the stock market, right? So basically, you have that, you have all of these instruments, let's say portfolio, and you basically want to perform almost almost as well as the best one in hindsight. So there are algorithms known for specifically for portfolios, we call it universal portfolio. So basically it kind of, in my mind, it kind of says that you, in general, don't need stochastic assumptions about nature. You can just have stochasticity in the algorithm. So there is something fundamental on there. There's a book by Yoav called Probability and Finance. It's just a game. The first part of it is probability without measure, and the second part of it is finance without probability. So there is something going on. I'm not sure what it is.
Yeah, question about open problem. Is the solution when you don't want this log 1 over epsilon, suppose everything's discrete, is the solution known for this problem? So to adapt to the sum of the square of the loss of every step.
Sum of the squares.
Yeah. So there's BT, right? Instead of defining this.
Okay. So for hedge,
Right.
it is known. There is
Right.
a paper by Chelabianchi and Mansour that basically shows a bound of that type, for two actually different bounds of that type for hedge. For normal hedge, not yet.
Okay. So the main challenge is to to deal with this differential equation. So what is the main supposed to take a limit of hash, right? What's the main challenge of getting the log 1 over epsilon distance?
So that is not the log 1 over epsilon is the easy part.
Okay.
Basically, because once you have a potential,
Right.
you just say the 1 over epsilon defines the tail of the potential.
Mhm.
So what is the challenge is showing that the potential doesn't increase. Right, the potential has to stay the same, whatever the adversary does. Okay, and that is something that requires. It's not enough to talk about the SDEs because the SDEs do make statistical assumptions. You have to go deeper into it and basically understand what is going on there with the next order.
No, my question was about this SDs. You said for SDs, they are like part expert kind of guarantees.
Is what?
So using the SDEs, you were saying that there are like part expert type of like guarantees.
Expert?
Part like expert, like not the distributions.
So basically what is done, I have actually slides on it, but basically what is done is you discretize it. So you have the potential, and when you're playing the game, the discrete time game that we are playing, you basically take the chord that is an upper bound, and you take the slope of that chord as the weight. And so it all works fine in the context of these bounds. The square root of t log whatever 1 over epsilon is no longer the challenge. The challenge is to replace t with something that is quadratic. Yeah.
Continuing with the stock market example, where the experts are saying predictive models, and would the adversary be like a competitor or
No, the adversary is basically the market.
market?
The market can do anything and you're guaranteed to do almost as well as the best. You have, you basically have a set of options and you don't know which one of them will work well. And there's no guarantee that the market is stochastic. And you still want to work as well as the best one in hindsight. And there are algorithms like that, like Kover's universal portfolios. Basically,
Grant Thomas book,
I
guess.
Yeah, so you made a very interesting point about the difference between the binomial games weights and the hedge weights.
Right.
Yeah, could you explain that again? So I'm
Okay.
capable of getting an intuition. So knowing the.
Okay, so think about the loss at the end,
Right.
or the potential at the end,
Right.
when you have the binomial weights. It looks like a step function, right? If you're below k, then you're good. If you're above k, then you're gone. Okay, so if you go with that function and you do the backward recursion, you get a function that is, that is not convex. It starts not convex and it continues to be smooth version of the not convex. When you do hedge or normal hedge, you don't know k in advance, so you can't basically at some point give up x. You never know if this one that is really, really bad right now might become better still. So you never really give up on that.
So that explains the tail that falls off, right?
Right. Basically, you're literally, when you're playing this game, you're close to the end.
Right.
Laggards, that experts that are really very far behind, that made very few mistakes, you have to give up on them. You're not trying to move them. Basically, you're trying to move all of the experts to be in the bad side. But this one is not acting, so you kind of give up.
Yeah, so one more question about the terminology. So you talk about drifting games. So the way it is drifting is because adversary can decide like why is it drifting?
Oh, okay. So to explain better why it is drifting, I need to go into boosting. So a very similar game can be defined for boosting. It's basically the game that is behind boost by majority. And there you have that the weak learners are giving you something that is half plus gamma. So a little bit better than I'm guessing. So that's the drift. Here it is with drift 0.
I see. So it has nothing to do with non-stationarity and has, people talk about online learning with competing with a sequence of changing comparators to track all kinds of non-stationarity. I was thinking is that, maybe drifting game, like drifting means that the comparators are drifting and you can still compete with that.
These are all special cases of drifting games. This is basically, it's an analysis methodology. So Rob Shapiro first did it for discrete, or basically you have like, what do you think about it? It's sheep on a meadow, and basically each sheep can go within some ball, at every step. But the sheeps in general, what the master can do, it can put a vector on each location, and the sheep as a whole have to be slightly correlated with that vector. That's the drifting game. That's kind of 2-dimension and so on. So there's more stuff there. Very interesting. Yeah.
Is it sensible to consider a scenario where the learner has access to some randomness that the adversary doesn't know about? You can play like a mixed strategy.
in the way that we're doing it, the mixing is right from the beginning, right? We give this probability distribution over all of the possible actions.
But you end up just like picking an argmax.
No, oh, no, it's defined to, the loss of the master at this time is defined to be the weighted average. So there's no random, of course you can add this randomness, but the game itself, so in this game, unlike the randomness, the fact that the adversary knows what is our potential function doesn't help it. So it's already at the min-max kind of boundary. Doesn't need more randomness. More randomness is basically like averaging. Okay. All right. Thank you very much.
Sorry, I didn't see you. I wasn't playing.